The first part of the problem, I say you have a solution of each material, quantum dot specific size, and you illuminate it with blue light. So just to give you a bit of a hint, what you can think about there is you can look up the wavelength of blue light, and blue light has a certain energy, and then based on our discussion in lecture, you should be able to think about how the light would interact with the quantum dots based on the numbers you derived in the upper parts of the problem. And then it asks you to think about what happens if you have multiple sizes or multiple materials in solution and the quantum dots get close together. And something that we didn't discuss, but I think will be helpful for answering the question, is that if you have two nanostructures very close together or in contact, you can imagine that an electron in an excited state in one of the structures might be able to cheat its way into the other structure and therefore find, you could say, the least resistance or lowest energy path back down to the unexcited state. And that's what I want you to think about when suggesting an emission spectrum for the solution when you have two types of structures in contact. And when things decay from an excited state, which can be above the band gap, they can decay non-radiatively until you reach that band gap, and then it's that lowest energy difference that's going to determine the energy and therefore the wavelength of emission. So of course you can hit a particle with any wavelength of light, and you need the energy of that light to exceed the band gap in order to excite the electron, and then the electron will decay down no matter how high it is. And in the case of the model that we're considering in this course, we're only concerned with emission at that primary first energy transition, essentially the effective band gap of the nanostructure that considers the band gap of the material plus the difference or the change in the band gap based on the quantum confinement. And also, as I think an earlier part of that problem, you're going to be looking up effective masses for holes and electrons. And in case you haven't realized already, the source you use might have a slightly different value, and you may need to pay careful attention to the way the values are normalized. For example, in some sources, they normalize the effective mass divided by the electron mass, which is like 9 times 10 to the minus 31 kilograms, I think. Just be careful of that. And as long as your values are about right, it's not going to matter to us which value you choose as long as you clearly state the number you chose. So those are the couple things I had in mind. Are there any other general questions? Yes?
So when we're determining the energy levels, the first 5,
yes?
So do you want us to go from quantum number n equals 1 and then L goes from 0 to 4?
So you basically have two indices, right? You have the Bessel function and you have the quantum number. The first 5 energy levels should be the first 5 values ranked based on your calculation. So they may not be necessarily in order of, you have two numbers you can index, like 10, 11, 12, 20, 21, 22. Like, there may not be a prescribed order among those. Just rank them by the energies that you find out. Other questions? Okay. So, of course, last time we continued our discussion of nanocrystals and quantum dots, and the main conclusion here is that as a material gets bigger, the band gap, effective band gap, decreases, and we approach the static band gap that we see in bulk materials. And we're considering this regime called strong confinement, which we don't talk about in detail, but here is where we can neglect effects due to coupling of the electron and hole, and that lets us adopt the simple model that we derived. And these are pretty good yet imperfect approximations, but for example, when we think about how to sketch a spectrum, if we thought, in the strict context of our model, what the emission spectrum would look like. If we have electrons decaying across one specific band gap, then all the photons are going to be emitted at a certain wavelength, at a certain energy. So that would mean that the spectrum is a delta function located at that wavelength, at that energy. But in practice, we would have a distribution of sizes and also other effects that would cause some dispersion in that. And that's something that might also relate to the problem set. It's not going to really matter if you show a delta function or you show a breadth, but that is really the origin of that smoother peak that we see in the real spectra of the materials. And then Aaron talked a bit about the origin of band gap and how that relates to the dispersion relation coming from solving Schrodinger's equation and adding other considerations, and that determines the allowable energy levels. Essentially, what came before our ability to say that semiconductors have this ability to emit light based on excitation of energy carriers in their structure. And then while the dispersion relation tells us the allowable energies, we can also consider that the probability of finding an energy carrier or an electron in a particular state and a particular energy is determined by a statistical distribution. So all these things come together to build a more comprehensive understanding of what governs the structure of materials and how they behave electronically. And then at the end, we saw a couple examples of what we're referring to as quantum size effects, the behavior of a single electron transistor, which is kind of like a regular transistor, but because our quantum dot, our island, has these discretized levels, has these quantum confinement, we can then design and operate that device so we can store a discrete number of electrons on the device at a time, and we see these jumps in the effective conductance, or the number of electrons per time, based on how much field we're applying to store charge or store electrons on the island. And then we talked briefly about how the difference in the metallic or semiconducting characteristics of single-walled nanotubes, this profound thing where we see them going from metallic or zero band gap to semiconducting or finite band gap based on these small differences, can be thought of at a very high level as the effect of the size on the confinement of the wave function and therefore the allowable energy levels. And from the qualitative picture we want to develop, we can see that resulting in an opening of the band gap or a band gap that is in function similar to that of graphite, which is a zero gap semiconductor. Okay, so today we're going to talk about mechanical properties, and for those of you who have a mechanical engineering or materials background, I think today's material might feel more at home to you. And I want to get down to the real basics of what determines the stiffness and the strength of a material, because at the simplest level, I think we can think of nanostructures as being individual atoms connected by springs. Those represent the bonds, and believe it or not, we can get some, to me, pretty cool and interesting insights based on just considering a bond as a spring. And we'll apply this knowledge to understand the mechanical properties of one-dimensional nanostructures, long, narrow things like nanotubes and nanowires, and we'll learn some aspects of their unique behavior and characterization methods. We'll talk a bit about the statistics of defects in small volumes. Basically, as the volume of a material gets small, in a bulk material, if you could count the defects, you'd find there's a whole bunch of defects. And the distribution is pretty uniform. But if your material gets really small, the volume gets so small that maybe there's only a few. Maybe there's just one. Maybe there's zero. And what happens if there's zero? There could be interesting effects on the material properties, and we'll go through some nice observation of that. And we'll talk a bit about other approaches to controlling strength of bulk materials by engineering them at the nanoscale, and we'll cover an example of how nature in some ways nanostructures materials to make them strong. And I have a set of papers up on CTools. I really want you to just read these two papers which talk about experimental and analytical aspects of measuring the mechanical properties of nanotubes. In this case, they're tungsten disulfide nanotubes and gold nanowires. And there's a lot of kind of basic stuff that's in the lecture discussion and also is in a supplement that I wrote up that has just been posted on CTools. There are some extra papers that talk about bulk strengthening. This is not highly important for the problem set and forward assignments, but it's interesting if you want to look at it. And then a couple of other papers for fun, one talking about flaw insensitivity at the nanoscale, like how natural shells are designed, and also we'll see what the nanotube radio is later. Okay, so can I see your hands if you're mechanical engineers? Okay, so that's the most of us. So of course, society has been engineering materials for a long time, and this kind of pictorial graph has time on the horizontal axis, and it lays out 10,000 BC over here up to, I guess they're going to 2020 here. And it's hard to see the small text here, but it's basically telling us a general trend of how industrialization and development of materials synthesis and manufacturing processes has changed and advanced the materials we've used. So these authors actually categorize materials of all time into four basic categories: metals and polymers or elastomers, composites and ceramics. But back in the day, we didn't use so many metals because we didn't have the bulk processing technology that happened in the industrial revolutions of the late 1800s and early 1900s. Things that we could refer to as polymers are really natural polymers like wood and animal skins and fibers. There were some composite materials made by taking different natural materials and mixing them together, stone and brick. And then they also had glasses and ceramics made by things like melting sand. And as time has gone on, we've developed a lot more engineered materials, engineered polymers, alloys of metals with higher strength or combinations of strength and weight that are useful for things like aircraft where weight is a demand. And now there's a lot more development in really engineering the nanostructure of materials to optimize their properties, to tune their properties, and also understanding the behavior of materials at the finest scale. And really a lot of that has been brought on by the characterization methods we know about now: electron microscopy, atomic force microscopy, X-ray analysis, and so on. I think we've in some ways reached the limit of some material properties, but in other ways we have a long way to go. And you can consider the more we understand about how to engineer materials and engineer their mechanical properties, the more we can fill in these large charts of going from, say, zero thermal conductivity to maximum thermal conductivity, or optimum combinations of stiffness and strength and weight. And that really improves the fidelity at which we can apply materials to useful applications. So as a simple review, most of you being mechanical engineers, this will seem very introductory. But the most perhaps basic way we characterize and understand the performance of a material mechanically is to look at what happens in a tensile test where we have a bar of material of length L under a uniaxial tension. So we apply a force to the material, and if we pull on it, we see two distinct regimes. So there's first what we call an elastic regime, where the stress and strain, stress defined as the force divided by the initial area, and strain defined by the change in length, delta L, divided by the initial length, are linear. And then we take the slope of this line and we give it a symbol capital E, and we call this the Young's modulus, or the elastic modulus. It's related to the stiffness of the material by the geometry, if we consider this to be like a spring. And then we call by convention, we say the point at which we have 0.2% permanent deformation, meaning the material is going to be 0.2% longer if we take off the load and let it relax. That's what we call the elastic limit, or the yield strength, sigma y. And then we can, depending on a lot more complex things, we can often pull the material more and we can deform it plastically, so cause irreversible mechanical processes to happen. And then at some point, the material breaks for good. It basically comes into two pieces or more than two pieces, and we've reached the ultimate strength. So you remember the difference between ductile materials and brittle materials. Ductile materials are ones that absorb a lot of energy or can have a large plastic deformation range. So something that's really stretchy is a very ductile material. And a brittle material is one that has very little plastic deformation, something like a piece of chalk that would snap because of the nature of its characteristics. And this can be a pure material, it can be a single crystal, or it can be an alloy, or as we'll see today, it could be just an individual nanostructure. And we certainly see some interesting effects based on that. And I think these slides we'll skip over them because it's more of a review. But in the context of basic engineering, we typically define the stress as really what's formally called the engineering stress, and we always divide it by the area of the cross-section before loading, and also what's called the engineering strain is typically defined as the length before loading. So as because of the coupling between the strain in one direction and you could say contraction in another direction, the Poisson's ratio thing, the area is going to change as we load it, but we typically normalize also because it's sometimes hard to measure the area at all times. And this very straightforward way to lay out stress and strain is what we're going to use throughout today's lecture. And we're just going to think about what happens as we shrink the size of the system down. And in addition to the simple case of loading of this uniaxial bar in tension, and we can have different types of loads, and we won't treat any of these analytically other than the case of simple tension. up at the left here, but we'll see some experimental aspects of how loading nanostructures in different directions, in multiple directions, can lead not only to tension, but to things like shear, where the strain is where you're basically moving the material at an angle in a direction that is parallel to the load, and also cases where you're applying, for example, uniform or hydrostatic pressure or bulk compression to the material. And we saw in one of our first lectures that because of the surface pressure, the effective surface energy, because of the dangling bonds around the surface of a nanoparticle, there's actually a very high internal pressure in a nanostructure, and this can change the lattice spacing or change the spacing between the atoms. We had a plot from experiments where we saw that for gold nanoparticles, and remember the change was really small, but it could still be measured using X-ray techniques that really precisely measure the spacing of the structure. And we'll also see an example today for carbon nanotubes where this sort of built-in strain, this built-in stress, can also effectively change the mechanical stiffness of the nanotube. And these changes are small, but they can be quite profound and interesting when we get to the small size scale. And things like nanotubes let us, we know chirality, we know how that relates to diameter, and because we can index them based on that, we see actually changes in the Young's modulus as the diameter goes down and based on the chirality and the orientation of the bonds with the axis of the tube. Okay, so I put up a few questions here. I'd just like to hear some of your answers or thoughts on these topics in no particular order. So if you have a thought, raise your hand and speak up. So pick the first one. So what determines the stiffness or the strength of a material?
Geometry and strength of the bonds.
Okay, the geometry and strength of the bonds. That's great. What makes some materials stiffer or stronger than others? Maybe a general answer, maybe say in the case of why are ceramics stiffer than polymers? Someone else?
Polymers have kind of coiled molecules that stretch out, so the bonds are extremely different than ceramics, which are usually ionic bonds.
Okay, so ceramics can be ionic or also covalent. So the type of bonding can affect the stiffness, as we'll see, and also the organization of the molecules can affect both the stiffness and the strength. Like polymers are typically like long chain molecules, like carbon fibers, for example, or you could say something like Kevlar, or the fiber that would be in a synthetic piece of clothing is made by making a polymer solution and spinning it out like you might extrude spaghetti, but at very high speed, and then treating it so you align those polymer chains with the axis of loading. And the type of those bonds, basically what atoms you have connected to one another, and the characteristics of that bond are going to determine the stiffness of the material, and the organization of the chains, and you could say the gaps between them, the sort of defects, can relate primarily to the strength of the material. Everything is coupled, but that's kind of a basic picture that we'll start to build upon. So if we think of a simple model of a material, let's start to build this picture that a material consists of atoms, as it certainly does, connected in a lattice, and each atom is bonded to a certain number of other atoms. And we know that we can have a bunch of different lattices, and that can change the picture. But now let's break it down to just having two atoms connected by a single bond, and then we'll be able to generalize that to some more macroscopic characteristics of the material. So the way we're going to start to do this formally is using what's called an interatomic potential. And the interatomic potential is a plot, or you could say you have a plot, you have a curve, you have an equation that relates the potential energy between the two atoms as a function of their separation. And in this case, we're calling R the internuclear separation, or the distance between the nucleus of one atom to the nucleus of the other atom, or the center of ping pong ball 1 to ping pong ball 2. And we'll pick up on how this picture is derived, or how this function is derived, in a few lectures when we start talking about van der Waals forces and intermolecular forces. But what we're going to use it for today is to get a simple representation for the stiffness of our bond. Because what happens as you play with this spring, say you're able to take your material, go in to a really small space and cut out just one bond, and you have the bond sitting at its equilibrium separation. And if you push the bond together, so you push the atoms closer to each other, you eventually feel a repulsive force. And this can be thought of as the electrons around each atom electrostatically repelling each other, pushing each other apart. And then if you pull on it, go in the other direction, you'll feel an attractive force, and it'll be like stretching the spring and feeling like the atoms want to go back toward each other. And this results from a longer range attractive intermolecular forces, which we'll call van der Waals forces and dispersion forces, and we'll see the origin and definition of those in a couple lectures. But the origin is not important here. What I want to say is that we can use, for example, a potential function, a function which basically tells us the curve of energy versus separation, and we can, for example, take the derivative of this, or a couple derivatives of it, and by linearizing this function around this static separation, we can say, well, here's about the stiffness of the material, or about the stiffness of the bond. So we could say, by definition, we have this U, which is a potential energy. So U is our interatomic potential. So the units of U are energy, which can typically be joules. So then if we take, say, a first derivative of our function, say du dr, so assume we just have our one-dimensional system, then we'll get a force, say in newtons, because a newton is just a joule per meter, because a joule is a newton per meter. And then if we take another derivative, we'll get a stiffness, say in newtons per meter. So you may have already seen this in the question on the problem set, where we try to consider the mechanical properties of the hexagon and give you the potential function. So by taking the first and second derivatives of these types of functions, we can get the idea of a bond stiffness. And there are many different ways that these functions are derived, but for now we can just take it as given. So and I'm going to call this stiffness S. So if we have a little picture of one atom connected to the other atom by a spring, and there's some initial separation, let's say x naught, then the force, say the restoring force, if I pull the atoms apart, is going to be just as we would say for a macroscopic, tension spring, the stiffness S times x minus x naught, times the displacement of it. And so now let's make another just very, very coarse assumption that this is kind of like a little bar in tension. And so let's define a cross-sectional area as equal to x naught squared, or approximately equal to x naught squared, or like, you have about one circular area of area radius x naught as the cross-sectional area of this piece. So then, if we go back to our classical definition of stress as force over area, which we know is the Young's modulus times the strain epsilon, then we know the force up here is the stiffness times x minus x naught, and the area is x naught squared. And then if we just kind of separate variables here, let's say we have S divided by x naught times x minus x naught divided by x naught. And so this looks exactly like our definition of strain of epsilon, delta L divided by the initial length. And then let's say that this is the very simple definition of the modulus, or our Young's modulus of our little nanounit cell here, our pair of atoms.
Okay.
So if we use this approximation to think about the Young's modulus of some materials, what we want to do is look at the interatomic potentials for different materials or different types of bonds. So as a generalization, it may be found that covalent bonds that are the stiffest have the strongest interaction because you actually have electron transfer, mating of the outer shells from atom to atom, have a stiffness S, which we'll say covers a generic range of, I'm going to write this better, 20 to 200 newtons per meter. Means you need to apply like 200 newtons to stretch an individual bond 1 meter. Wouldn't actually stretch that far, but as a picture. And then metallic or ionic bonds, where electrons are more globally shared and there are these free electrons moving around, are less stiff. So say 10 to 100 newtons per meter. And then in polymers, I'm not saying there's a polymer bond or a polymeric bond, but polymers typically have much less stiffness, say 0.5 to 1 newtons per meter. So then, if we go back to our idea of this Young's modulus as being our stiffness S divided by x naught, and we say that x naught is maybe 0.2 nanometers or 2 angstroms. So remember the carbon-carbon distance is about 1.4 angstroms, so we're about right here. And say we have a material with our stiffest bond, so 200 newtons per meter. Say that represents a carbon-carbon bond, because the covalent carbon-carbon bond is one of the strongest that's found. So if we solve this, would have 200 newtons per meter divided by 0.2 times 10 to the minus 9 meters, which is 10 to the 12th newtons per meter, which is 1 terapascal. So like 1,000 gigapascals. And maybe the numbers here were chosen to make it work out right, but these numbers are very realistic, and it turns out that 1,000 GPa is the stiffness of hexagonal carbon of graphite in plane. So if you have a perfect graphene sheet and you pull it and you define the thickness right, or better yet, if you have a block of graphite and you pull on it and you're connecting to all the sheets nicely in parallel, then you're going to have a Young's modulus of 1,000 GPa. So in comparison to this model, or this, say, limiting value for graphite, which is probably one of the stiffest, if not the stiffest material we can think of, why do polymers have such low stiffness? Maybe getting back to what's bonded to what inside a polymer. Anyone give it a guess?
The bonds between polymer change are primarily due to van der Waals forces rather than stronger ionic or covalent.
So you certainly have that effect, and you also have the effect that in a polymer chain you have different types of bonds. So you might have some carbon-carbon bonds, and you might have some much weaker bonds like, say, carbon-hydrogen bonds. And if you think of a material as a chain of springs, then the weakest bonds are going to dominate. So if you think back to, say, how if you had, say, 3 atoms in series now, and we had 2 different bond stiffnesses, and we derived the effective stiffness of this series combination of springs, then we would see that this is equal to K1, K2 divided by K1 plus K2. And then, if K1 is much less than K2, then the K1 goes away from the bottom, the K2s cancel, and this gets to K1. So the weak links in the chain are going to dominate, and that, in addition to the interactions of polymer chains, are why polymers, for example, even though you might have some really, really stiff carbon-carbon bonds in the chain, can be a lot weaker, and so on. And that it can mean the material properties are a lot weaker, but it also provides a lot of design freedom. In polymers can be really stretchy. You can stretch a plastic bag a lot before breaking it. So you are actually aligning and reconfiguring those chains when you stretch out a piece of polymer. And there's so much more in that in the area of polymer design and kind of polymer theory. So sorry, I'm missing a slide here. So now let's think for a moment about strength in addition of stiffness. So it turns out that like the stiffness or the Young's modulus of a material can be pretty close to the theoretical limit. If you take the value of the bond stiffness and you compare it, for that value for, say, metals, and you compare it to, say, the Young's modulus of steel, which could be about 200 to 300 GPa, you get an answer that's pretty close. However, strength is typically a lot lower than this, kind of a generalized theoretical limit. And that's because strength of a material is governed by these interactions, by imperfections in the material at larger scale. So things like defects and grain boundaries and all those details are sort of beyond our scope, but there are a lot of mechanisms by which materials deform, and that mean that the strength or the larger scale deformation and the stress at which the material fails is governed by other aspects of the organization. So, typically if we looked at just this one bond, and we went back to the interatomic potential, we could say that maybe at about 10% of the separation, or say at about 10% elongation, the atoms would no longer feel each other. So we could say, well, that means that the bonds are going to break at about 10% elongation. So that if they broke at 10% elongation, and we went back to our original expression for the stress, where we had S over X naught times the strain, and we said they're going to break at where strain is about 0.1, then that would very directly tell us that they'd break at about 0.1 times the Young's modulus. And if we look at the real world of materials, very few things are close to this limit. It's more typical that materials will fail at 1/10,000th or to, say, 1% of the Young's modulus. And that relates to how the materials are organized and how defects propagate through them. So we previously saw this chart that lays out, it's designed to look at materials with high stiffness and high strength per unit weight, but it can also apply to this discussion because everything's divided by its own density. So we can see the kind of universe of materials here. And there's the arrow. So things like foams and polymers have relatively low strength and low modulus or low stiffness, and metals get a bit better. And composites combine attractive attributes of different materials and kind of push this out farther. And so if we look at this chart and we plot lines of constant values of sigma divided by modulus, so here I'm saying strength divided by modulus, you can see that our theoretical limit of 0.1 is not approached within an order of magnitude by many of these materials. And in fact, things like measurements of individual nanostructures, individual nanotubes, can, there's a lot of variation in those measurements, and we'll see the origin of that later, but there we can almost get to this theoretical limit where some researchers have measured carbon nanotubes that fail at a tensile stress of 100 GPa or 0.1 TPa terapascals, which is 1/10 of the axial modulus of graphite. And because of their organization, their microstructure and their nanostructure, most bulk materials are beneath this limit. Likewise, fibers made out of nanotubes by putting them together, and this gets to a topic we'll talk about a lot later, are even more significantly below this limit than some other bulk materials. And advanced fibers, for example, highly engineered polymers where the chains are really, really oriented, or where you start out with a long chain polymer and orient it really well, and for example, bake it out at high temperatures to try to convert that to a very high quality graphite, can also kind of get toward this limit. And that's because of the low density of carbon, and because of this ability to engineer high strength and basically tune the properties. We've seen a lot of effort in an area and application toward composites. And you can see that some advanced fibers can have modulus exceeding that of steel and strength exceeding that of steel, although it's much more expensive to process those per unit mass. So now let's start to think about how the properties of nanostructures may be different. Because if we can think about the individual bonds as comprising this material, and we can think about how the bonds might behave in different configurations, we can start to build this picture and maybe see why the nanotubes are as close as we've been able to get toward that theoretical strength limit. But so first we might need to think a bit about also how the mechanical properties of nanostructures are measured. In fact, the first time that scientists measured the Young's modulus, or the stiffness of a nanotube as a beam, they did it in a TEM, a transmission electron microscope, by watching the thermal vibration of the nanotube in the microscope. So they were able to heat it locally and change its temperature. And when the atoms get thermally excited, and we'll see more of the reasons for this in just the case of heat transport and conduction next time, the beam wiggles, and everything has some thermal vibration. But if it's a really small structure and the thermal vibration can be a prominent effect, they were able to measure the amplitude and the frequency of the vibration at resonance, and they were able to relate the average amplitude, or the mean square amplitude of this vibration, to the temperature, and then using a derivation for the amplitude of vibration of a beam as a function of temperature, they were able to relate it to y, which is the symbol here for the Young's modulus. So the details of how this is derived are not important for us, but this was the first way that researchers actually extracted the Young's modulus of a nanotube and got the answer that the effective modulus, considering the shell of the tube, is very close to that of graphite, or this value of 1,000 GPa, or 1 terapascal. And we'll think more about carbon nanotubes as beams in a minute. So I just wanted to interject a kind of cool application of the resonance of carbon nanotubes. Alex Zettel's group at Berkeley, that does a lot of creative things with nanoscale devices and MEMS, made a radio using a nanotube, where here you're seeing a similar picture of a nanotube in a microscope, and they actually used the nanotube as the antenna. So they were, when the nanotube disappeared, it started resonating with the broadcast signal they were providing with the Beach Boys song, and it picked up the song and then converted the mechanical vibration into an electrical signal using a circuit that's described in the paper if you want to look at it, and it worked. And the reason it worked is because the mechanical resonance frequency of this little structure was in the range of the radio frequency they were able to broadcast. And so this generally relates to the mechanical properties of the ability to consider these structures as beams, and they go through the resonance properties and the derivation of the resonant frequency, which you can check out if you want. So I've sort of built us up to think that we can consider a nanotube or a nanowire as a beam, as just like a macroscopic cantilever, the same kind of picture that comes from basic mechanics class. And it turns out that that's totally true unless you get down to really, really small structures, or unless you deform the nanostructure in ways that go beyond the conventional elastic limits. So, but just to say a couple important things about this picture, we do have to consider what the effective properties of the nanotube are. Basically, if the wall of the nanotube is made out of graphite, then we have to think about, well, what's the effective thickness of the wall? Is it like 1 atom thick, or is it 1 atom thick plus a little bit, based on like how far the walls will be apart, and so on. And so that's the one thing that we want to realize when we apply this basic cantilever beam model to something like a nanotube. So from back in mechanics days, if we had a cantilever beam with a force F at the end, and we deformed it so it had some deflection at the tip, and we called this tip deflection delta, then solving the beam equation would tell us that delta is equal to the force times the length cubed divided by 3 times the Young's modulus times I, the moment of inertia. And I for a rectangular beam is 1/12 times BH cubed, where this is B and this is H cubed. And I think for a circular beam, where you have, say, an inner radius, an outer radius, I forgot to write this down, but someone correct me if I'm wrong, is it 1/64 times, is that right?
I think it's pi over 4. I'm not sure.
Pi over 4, even with the diameter?
No pi's involved somewhere.
Pi?
It's pi over something.
Okay, I think it's pi over 64. I'll check that. Sorry, I forgot about that. So then the question is, like, if we have a nanotube, we have a single layer of atoms, what do we define as the outer and the inner diameter? Or basically, what is our wall thickness? And it turns on that going through a treatment that's like beyond the scope of what we want to do, we can basically assign for most nanotubes this wall thickness for a single wall nanotube to be twice 0.34 nanometers, where 0.34 nanometers is the interlayer spacing of graphite. So, because you have 2, if we're in diameter here, you have 1 interlayer spacing here and 1 interlayer spacing here. And if we do this, we're able to apply a Young's modulus of 1 terapascal. And then we can, in the linear elastic regime, we can model our little nanotube beam as a regular cantilever. And as a convention, I like to think that if we say we have a 1 nanometer diameter nanotube, that to me corresponds to the middle space between there. So if you said where are the nuclei of the atoms, we're going to say they're right in the center here, and like the inner diameter is the diameter that we're quoting as the diameter minus 0.34, and the outer diameter is that diameter plus 0.34. And this becomes more important if we think about multi-wall nanotubes, so nanotubes that have multiple shells. And it turns out that by doing some more thorough calculations, we can derive that the modulus of a nanotube can relate to its number of walls because of the coupling between the walls and the effective spacing. And if you end up with a nanotube that has a very large number of walls, you end up with a result that just drops out to the result for deforming a stack of graphite, because the hole in the center of the nanotube isn't so important. But if, for example, we have this nanotube which is hollow, if we bend it, then this bending model is considering that we have a hollow structure, and therefore we're effectively accounting for the material that's missing from the center. On the other hand, if we imagine that we're deforming the nanotube in tension, we also have to make a similar correction for the effective area. So we basically have to only count that we have a hollow beam and a hole in the center. And this is a pretty straightforward thing to do, but I think it's interesting to see what happens if we build a little spreadsheet to calculate the effective axial stiffness or effective axial modulus of a nanotube. So if here we had a nanotube that is hollow, has one wall, and we're pulling on it in tension, people say that, well, the stiffness of nanotubes is 1 terapascal. Well, you can't forget about the hole in the center. And so if you have, say, a 1 nanometer diameter tube and give it a nominal wall modulus of 1 terapascal and a thickness of 0.34 nanometers, and then if it's 1 nanometer diameter, the effective modulus of it, because you have space in the center, is only half of that. If it's, say, 2 nanometers diameter, then it drops down to a bit less. So you can see that because of this empty space in the center, if you imagine having a perfect cable of nanotubes packed together, the modulus of that cable is not going to be 1 terapascal. It's going to be a fraction of that. Plus, we have to think about the extra area that's also lost as we pack them together. And we consider effects of these kind of chain orientations and so on. And we'll learn about the practical aspects of that when we think about fibers and assemblies, which is a topic for after the exam. But even these simple kind of geometric considerations of hollow beams and so on have to be applied when we think of structures at the nanoscale. So another thing that turns out is that for carbon nanotubes, the modulus of the material, so the effective modulus of our wall, depends somewhat on the chirality of the tubes. And this is because of a couple of effects. One effect is that, imagine we thought about rolling our graphene sheet into a nanotube, and when we get down to really small nanotubes, the strain in the bonds actually matters. Or basically, we have a lot of strain that's caused to curve the bonds and deform them from their equilibrium planar orientation. And because of, you could say, that stored strain energy, the material is less stiff because we're actually pre-straining the material in a direction other than the direction we're going to load it. So here is a plot of the effective Young's modulus in terapascals. So you could say this is about 1. This is 1.04, but we can call it 1. And although these effects are small, we're down by a few percent here, we can see generally as the diameter goes down, we see a decrease in the Young's modulus. And mind us here that the diameter of 10 angstroms here is 1 nanometer. So we're talking about really small nanotubes. But I think it's interesting to think about this effect, or that the built-in deformation of the material can affect its mechanical properties. And these are all done by some computer calculations where they used a particular potential function called the Tursoff-Brenner potential, named after the guys who brought it up. And this is just basically a potential function that is like the potential curve we saw earlier, but is more complex and represents the potential in some different dimensions. And so the other thing we see here is that in addition to the diameter, the modulus also depends on the chirality. And this tells us that generally armchair nanotubes are less stiff than zigzag nanotubes, having approximately the same diameter. And this has to do with the orientation of the lattice with respect to the axis of loading. And effectively, you get a different modulus if you're pulling on a tube that has bonds oriented this way to pulling on a tube that, imagine you have the bonds primarily parallel to the axis of loading. And these are small effects, but in one of the problem set questions, I ask you to look at how the modulus of different nanotubes of different chiralities might be different, and these are the kinds of things that I want you to think about. So in addition to that, you could say, the first crude method of watching the nanotube resonate and relating its resonance amplitude to temperature. There are other ways that people measure the mechanical properties of nanotubes, and in fact, they use microtechnology or MEMS technology to build small tensile testers that are analogs to the big tensile testers that are used to test macroscopic materials. So this is a picture, I forgot to put the site, it's from Horacio Espinosa's group at Northwestern. They do a lot of nanoscale mechanics, and they used microfabrication to build a silicon device that contains an actuator to pull on a nanostructure and contains some capacitive electrodes to sense the displacement, and therefore, knowing the stiffness of the structure, you can measure the load. And they do tensile tests on individual carbon nanotubes. So the nanotubes are made elsewhere. They're able to place them across this gap, and then they actually deposit some carbon, some additional carbon, which acts like a glue, just like you might glue a piece of polymer fiber down with epoxy. It's kind of like nano epoxy. And they're able to do tensile tests, and they normalize them based on the dimensions, because they can also put this in a TEM, and they can measure its diameter, and they can other stuff in this paper, if you want to look at it, they actually look at how the tube breaks. But you can measure the diameter and calculate the stress, and measure the length and calculate the strain. And they get measurements of the linear elastic deformation of individual nanotubes. And they use different approaches to modeling the displacement. But the interesting thing here is you can see that the stress that they've calculated in these nanotubes, so normalizing for the inner diameter and the outer diameter, is reaching about 10% of the modulus, or about 100 GPa. And there's also, kind of a distribution in the moduli and also the breaking strengths of these different tubes. And this distribution gets to the statistical aspect of failure at the nanoscale. Failure is statistical at any scale, and if you have 10 bars of brass, they're not all going to fail at the same stress. But it becomes even more important when you get down to a small volume where the number of defects may be greatly different because you have such a small chance for only a few defects to accumulate. There are also some other interesting things about.
I have a question. Do we have a defined concept of a Poisson's ratio here, similar to bulk materials? For a single wall nanotube, how does that effect work out?
So that's something that's still under study. Like you can, the question is, can you apply the same concept? Well, certainly you could. You could say, you could define Poisson's ratio as the axial strain divided by the lateral strain. And I don't recall what it exactly is, but I think for nanotubes, you'll see a contraction of the diameter as well, and you'll also see in some cases a kind of dislocation glide, as we'll see in a minute. So there are different kind of modes of deformation in other directions.
The plasticity curve in the C.
I'm sorry?
How do you explain the plasticity, the leveling off the curve?
Are you asking about this graph or this graph?
C graph.
This graph?
Yeah.
Okay, so these are models that include some kind of plastic deformation, and in this case, the nanotubes fractured or broke in more of a brittle fashion. So that's why this experimental curve is departing from the curves here, but it's matching the first regime quite well, and they go into the details of these different models a bit in the paper, and I think in their other papers. So there are some other interesting deformation modes and results for nanotubes, and one is that you can buckle and kink the individual walls. And one thing that happens is that, if we imagined our nanotube as a cantilever beam, based on the way that the stress is distributed in the material at the nanoscale, if you have a multi-walled nanotube that has a whole bunch of walls, in this case, this is maybe 50 nanometers or so, so this is more than 100 walls. If you have 0.34 nanometers per wall, there's a point at which the nanotube gets so big and that you actually induce these kinds of ripples by buckling of the inner walls on the inside of the tube. And this effectively is an instability and leads to an effective decrease in the bending modulus of the tube. So if you, for example, deform the tube by a certain amount and this buckling happened and you extracted an effective modulus, you'd find that the modulus is much higher, is this ideal 1 terapascal value for small diameter tubes where this buckling doesn't happen. But where the buckling does happen, the transition is about between 10 and 15 nanometers. This instability causes the tube to be a lot less stiff and kind of kink down. And there are some other interesting things that happen. And because of the interest in nanotubes, it's kind of served as a model material. But this happens with other tubular nanostructures. In a similar vein, you can also kink carbon nanotubes kind of like you would kink a straw. And there have been observations of that, for example, in a microscope. In fact, if you take a sample of nanotubes that you've grown, at some point you can usually find a nanotube that's been kinked. They either kinked during growth or kinked when you're preparing the sample, or so on. And also kind of analytical atomic scale modeling where you can see that there is this kind of instability that happens as you bend the nanotube. They're defining this angle theta. Then it snaps over and relieves some strain energy by buckling and kinking like so. And it turns out that people have shown computationally that when you kink the nanotube, in some places the atoms actually reorganize. They will move around to relieve strain energy, and when you unkink it, the atoms move back. So this is kind of like a reversible deformation of a little nanoscale structure. And you can go on and on as to what computation will show, but it shows interesting things like you can, for example, if you ideally perfectly axially compress a nanotube, you can get these other interesting deformation modes. And although it's could say hard to measure this experimentally, or for example to perfectly load a tube or to configure it like that, the hope and the interest here is that by exploiting these unique kind of instabilities, we could make interesting and nonlinear mechanisms. So things like little robotic flexures or actuators that could deform in unique ways and last for large numbers of cycles. For example, if this atomic kinking process is reversible, you could imagine a material that will kink over a large strain, kind of like an elbow, without fatiguing or without getting in arthritis in the joint. And maybe that's possible if we could build the mechanisms to hold it and if we could study it over a long cycle time. But there are certainly some interesting mechanical aspects. And another interesting aspect that's been studied with nanotubes is, we talked about how they elongate and kind of, fail in this kind of brittle fashion when we strain them at room temperature. But if they're strained at elevated temperature, in this case, that's what was done. The researchers put a fairly large. They were able to take a multi-walled nanotube and kind of cut it down. So they only had one wall remaining over a portion of about, say, 50 nanometers. So this is maybe 20 nanometers by 50 nanometers, and it consists of a single layer of carbon atoms. You wouldn't grow a single wall nanotube like this, but they were able to make it in a very careful way. And then what they did is they heated it by passing a current through it, and they also stretched it. And they did both of these things while watching it in the TEM, and they were able to make it behave like a rubber band, or like you could say a piece of polymer that you're heating and stretching into like a long string. And in fact, they showed that this nanotube had what people call superplastic behavior, or it deforms a lot without breaking at very high temperatures. And they estimated that they were about above 2000 C. And because this is in vacuum, the material is not going to degrade at this temperature. This would be stable to, I would say, close to 3000 C. And they got a huge elongation over close to 300%, and the diameter decreased by over 15 times. And others have related, perhaps not exactly this behavior, but the plastic deformation of nanotubes under elevated temperature to actually the motion of dislocations or defects in the structure. So from the idea of macroscopic deformation of materials, people talk about different types of dislocations, gliding and moving and grain boundaries restricting dislocation motion. Well, that concept also applies at the nanoscale, and in the case of nanotubes, it's just that we have kind of a different lattice, and we have different types of defects or dislocations. And the one that we've seen before is this Stone-Wales defect, where instead of having you take a little zone of the lattice, and instead of having 4 hexagons, you have 2 pentagons and 2 heptagons, 5, 7, 7, 5. It's been shown that the necking, this reduction in the diameter of the nanotube, is actually accommodated by by propagating transformations of these 5, 7, 7, 5 defects. And actually what is happening is you have the bonds rotating and moving the 5 and 7 and 7 and 5 over one more unit. And as these defects move, they stitch the nanotube down by 1 unit, basically take 1 atom out of the lattice, and you could see the chirality in this model here is going from 10, 10 to 10, 9, and it's pretty certain based on this theory, which is maybe about 10 years old in experiment sense, that this is the mechanism by which nanotubes will decrease their diameter as they're elongated. So you could imagine kind of like an analog to Poisson's ratio here, saying, well, what's the strain in this, in the radial direction versus a strain in the axial direction? But there are some, there is also a different way to look at it. And if you had many defects or missing atoms or extra atoms, you may not always have this perfect like 5, 7, 7, 5 thing, but the motion of the defects and effectively that you could assign a dislocation direction here is what governs the deformation and change of shape. Question in the back.
In zigzag as well as armchair, or is it specific to chiral?
As far as I know, it would happen in all nanotubes, but maybe the orientation of the defects could change. So now let's start to look at a slightly different material, and also a different means of measuring it. So we don't want to restrict ourselves to carbon nanotubes, although they're kind of a diverse example that a lot of the work's been done on. So this paper, which I think is one of the ones I've asked you to read in the main set, is measuring the mechanical properties of gold nanowires. And in this case, they make gold nanowires and suspend them across a gap. And maybe this is about a micron or less, and we can see the wire diameter down here is maybe tens of nanometers. And they're measuring the mechanical properties by deforming them using an AFM tip. And remember how AFM works, you have this sharp tip, and you can press down on stuff, and now knowing that you can bounce a laser off the surface, and they can basically measure the vertical displacement of the tip, and they can use that to model the nanostructure as a beam suspended from 2 supports, and they can measure its displacement. And they press it on here, and they actually anchor it down using that kind of glue like we saw before. And so the plots at the bottom are their measurements, and what the paper did that was really interesting and the first of its kind was they were able to measure the modulus, the Young's modulus, and the strength, or the stiffness and strength of the wires as a function of their diameter. And it so happened that there's always some spread in the data because of the uncertainty in the measurements and so on. But they found that the modulus really didn't depend on the size of the wire and was almost more or less exactly what is known for bulk gold. Bulk gold has a modulus about 1/3 that of steel, or about 80 GPa. And this is because the stiffness of the bonds being the same at the nanoscale versus at the macro scale, determine the stiffness, and that's why these agree. However, when they looked at the strength, or the strength, specifically the yield strength at which the material started deforming plastically, they found a really interesting trend. First, the strength of these nanowires was way higher than the yield strength of bulk gold. Gold is a pretty soft material. You hear about, you can like bite into it and see if it's real gold because it's soft, because you'll see your tooth mark in it. Well, its yield strength is way less than 1 GPa. And they found that the yield strength for all the sizes they studied was much higher than the bulk limit. And also, as the wires got smaller, the spread of strength values got larger, but the average strength went up. And this relates to the case of having fewer defects in the material and fewer flaws. They can be missing atoms, they can be vacancies, or they can be dislocations. Basically, the grain structure is changing as you go down to these small volumes. And this behavior will depend on the material you test. And the other interesting thing to me here is that we see the material approaching this limit that I proposed of strength being about the Young's modulus divided by 10. So here we can say that this wire is yielding by actually deforming the bonds until they fail. And our strength is not limited by other aspects of organization of the material. And it's certainly a big difference between this scale and the macro scale. So there are lots of types of nanotubes and nanowires, and based on the synthesis of the structures and the interest in the structures, folks also measure the property distributions. So this is a snapshot from the other of the two main papers, and here the researchers are using a scanning probe tip inside an SEM to do tensile tests on tungsten disulfide nanotubes. Here, what the focus of this paper is two things. One, they want to understand the statistical distribution of strengths in the material. So as I said before, every material has a statistical distribution of strengths, and here they're able to plot out the in a very relatively organized fashion a distribution in the probability of failure as a function of the applied stress. So F, the failure probability, is basically the probability that a material will fail at a stress equal to or less than the applied stress. So if you choose a stress which is really high and that it's going to make all the materials fail, then your probability of failure is 1. If you choose a lower stress, then your probability of failure might be 1/2. And this is formally this plot is what's called a Weibull plot. Perhaps from undergraduate mechanics you remember Weibull statistics, and they fit the Weibull relationship, which is a line when you plot the axes between F and stress like so, and see that it's a pretty good representation. And also from the raw data here, you can see that there's a pretty big range in the strengths of the wires. It may depend to some extent on size, but for example here, you have a 36 nanometer diameter wire that has a strength of 16 GPa and a 30 nanometer diameter wire that's like 10 GPa. That's a 60% difference. That's a pretty big difference. That's more than we might see exists for a macroscopic material. And the other thing that you'll read about in the paper that they do is they try to develop an analytical model for relating the strength that they measure, in this case the strength in GPa, to what they believe is the number of missing atoms, or what they're calling critical defects in the structure. So from what I remember, they're not able to actually measure the number of defects in one of these structures, but with reasonable confidence that they describe, they develop a fit between the strength and the expected number of defects, and a model which relates the failure stress to n, which they refer to as the number of defects. And they say that sigma c is an experimentally determined value for the ideal strength of material, and you can think of this kind of like a macroscopic crack mechanism. Remember, in like stress concentration, we had the radius of a crack A, and here they're calling rho the radius of rupture, and A is another characteristic length that corresponds to the lattice parameter, or the size of the rupture relative to the lattice parameter. And here, as the number of defects or missing atoms gets larger, the strength goes down and reaches an asymptotic limit, like so. And there are a number of approaches like this, and this is not highly exact, but what we can see here is that the strength of the material depends on the number of flaws in it, and that is an interesting and profound effect that's observed at the nanoscale. So I like to think there are kind of like two approaches or two perspectives on like engineering the mechanical properties of materials by nanostructuring. Like in the first part, we've talked about how materials are individual bonds and how that inspiration can let us to explain the differences in the measured mechanical properties of nanostructures versus macrostructures, and how stiffness might be close, but strength might be different. Another kind of means of engineering materials to control their mechanical properties is kind of a top-down approach, or one where you adjust the grain structure of materials. Basically, you have a bulk material of a piece of metal, and if you zoom in it with a microscope, you're going to see it's all these little connected pieces. And when we talk about defects and dislocation, we talk about the motion of the individual pieces of material with respect to one another before you've applied enough load that would actually break the individual bonds. And it's possible using processing techniques for a lot of materials to manipulate the average grain size. So here are some micrographs. I think these are TEM images where they've taken very thin slices of material, where these researchers who have written one of the extra papers have decreased the grain size from average of 150 nanometers down to 40, and then 20, and then 6 nanometers. And you see more order, more kind of polycrystalline character represented by these dots at the larger grain size than you do in the smaller grain size. But the basic idea here is that we see an effect of the grain size on the strength of the material. And if we add more grain boundaries, we might add more resistance to motion of the individual pieces and therefore increase the strength. So there's just one relationship or equation that I want us to look at, and this is what's called the Hall-Petch relation. Maybe you've seen this before, but this says that the yield strength of a material is equal to some constant sort of material-specific starting stress plus a factor divided by the square root of the average grain size. So we're not really able here to relate this to many other things, but this has been studied for a long time, and it says that as you increase the number of grain boundaries, the density of grain boundaries by decreasing the grain size based on the values of these constants, you gain some increase in the yield strength. But what's happened recently in research is as we're able to manipulate grain size to smaller scales, we find that there are some interesting and complex trade-offs in the characteristics of the material. So people have studied this for different metal alloys. This just shows nickel and tungsten and copper. And basically what's happening is now that we're able to control the grain size of these bulk materials down to regimes of, say, tens of nanometers, we're finding that there's a lot more opportunity to engineer the properties, but principally this idea of grain size strengthening materials breaks down because you can have more slip between the grains, and also because of the being so much surface. Imagine the material is like a whole bunch of nanoparticles pressed together. You actually have more diffusion of the atoms under deformation. And so this plot is kind of messy, but what we're seeing here is the hardness, which is in some ways a measure of strength, as a function of d, the average grain size. And we're seeing that as we decrease the size of the grain, we're making the material harder, and then there's a point at which things go the other way and the strength starts decreasing. And why this happens beyond the qualitative reasons I discussed is not something we'll study, but I just wanted you to see that this is still a very open and interesting area, and perhaps there's some interesting potential to engineer the characteristics of the materials. And another one of the optional papers talks in general about kind of strategies for engineering the boundaries of materials, engineering the grain boundaries. And there's this idea of cutting it up into individual grains, so you kind of you understand the deformation of the material by the motion between the individual pieces of it. And by controlling the types of boundaries having their basic what are called regular grain boundaries, where you have essentially two, you could say, pieces of lattice that are next to each other. And there are also what are called twin boundaries, where you don't formally have two separate pieces, but you have a boundary which is just a mirroring of the lattice, but you have one continuous piece. And what these researchers are talking about is their research and other research is saying that you can get different types of properties based on the types of boundaries that you engineer. And one of the classical things that happens when you decrease grain size in the regime that you strengthen the material, the strength goes up, but also things like the toughness or the amount of deformation you can achieve decreases. For example, the elongation to failure decreases. Essentially is a more brittle failure. But what they've shown is by putting these different type of grain boundaries, or they're not grain boundaries, they're twin boundaries, in a material, you can actually get more elongation to failure in addition to more strength as the grain size goes down. So here they're comparing the results of the two approaches, the twin boundary strengthening and the grain boundary strengthening, as a function of grain size, and they do about the same in this case for yield strength, but they do dramatically different things in terms of elongation to failure. So the mechanism is beyond scope, but it's interesting that indeed engineering these interfaces is important. And if you're interested in mechanical properties, something like this, thinking about how to engineer a material for specific properties might be an interesting topic for a project. And we just have a couple minutes left, but I wanted to also emphasize, as we build upon the idea of individual nanostructures to collective assemblies of nanostructures, that we can also see interesting properties when we put nanostructures together. A practical issue is that it's hard to pack individual structures perfectly together, and we may also see different properties as we have assemblies versus isolated ones. So this is an example of some research where vertically aligned arrays of carbon nanotubes were shown within a certain diameter range and spacing range to behave kind of like microscale springs. So here, if you take one of these vertical nanotube films and compress it, you can deform the nanotubes collectively so they buckle individually, but they have this kind of wave-like behavior. And the periodicity of this was about 12 microns. I think the diameter of the tubes is 50 nanometers. And the bottom line here is they show that this can be a very effective energy-absorbing material. It can deform by very, very large strains. In this case, their initial cycle was 85%, and this is the loading path. And based on the buckling, you see this is classic kind of foam-like behavior. You see ripples every time one of these buckles generates, and then when you unload it, there's basically a big empty space here, which is a lot of energy absorption. And so this is another possibility that has been used. So basically taking advantage of the individual nanotubes' characteristics of being able to kink and unkink, and collectively combining them into this foam that, if you looked at the modulus, it would be nowhere near the modulus of an individual tube, but this ability to elastically absorb a lot of energy, or maybe turn it around as an actuator or an impact absorber, could be quite interesting. Okay, so it's 12 o'clock. I'll stop here, and I'll have a couple of examples that we'll be able to use as a recap when we meet again on Monday.